So we are live. So good morning, everyone, or good afternoon, I should say. My name is Jesse, and I am with Exploring by the Seat of Your Pants. For those joining us for the first time, and we do have a few classes fitting that bill today, we are all about bringing conservation, adventure, and science into classrooms around the world. And we are particularly excited this month of October. Not only is it our biggest month ever, where by month's end we will have done 60 sessions with amazing researchers around the world, but all month long we are celebrating space. So we've had talks with astronauts, astronomers, engineers, technicians, and more. And today we're going to learn a little bit about space in an entirely different way. And I'll introduce our speaker in just a minute. But right now we've got 5 classes joining us from across North America. So I want to give them a chance to say hi and show how excited they are. So we've got Miss Coolins, grade 9s and 12s in Brantford, Ontario. Hi, guys. Hey, you guys are exceedingly enthusiastic for a high school group. Way to go. We've got Miss Wafer representing the Laurel Springs School with kids all around the world. Hi, Miss Wafer. How you doing? Excellent. All right. We've got Miss Eugenio's grade 9s in Toronto, Ontario. Hi, guys. Hey! Holy, we got like the best grade 9 classes ever today. I love it. We've got Mr. Candella's grade 8s in Kingston, Ontario. Hi, guys. Very Ontario group today. This is exciting. Hey, there we go. Welcome in. All right. Just get your mic muted again. And last but not least, we've got Miss Meineke's grade 3s in San Antonio in Texas. Hi, guys. Hey, always love Texas classes. All right. Of course, the reason you guys are all here today is for our speaker. So we are joined live 2 kilometers down in Sudbury, Ontario's SNOlab. So Sudbury Neutrino Observatory Lab by Dr. Erica Caden. So she's a researcher there and an educational coordinator. And she's going to explain a little bit about what that amazing facility does in understanding some of the deepest mysteries of our universe 2 kilometers down in a mine. Why would we be down there? What are we doing down there? What kind of research is going on? And so without further ado, I'm going to turn it over to Erica, old pro at this. And without further ado, here you are. Thank you so much for joining us, Erica. Take it away.
Hey, Jesse, it's great to see everyone. Thank you all for joining us. So yes, I'm not sure if you can hear all of the ambient noise. I am in SNOlab, so I am currently 2 kilometers underground. You can maybe see, it looks like I'm in a mine. So I'm actually right in between 2 experiments right now that are searching for dark matter, and I'm going to tell you a little bit about dark matter. So as Jesse said, for Exploring by the Seat of Your Pants, it's Space Month. For us, it's Dark Matter Month. So I'm going to quick share desktop. Perfect. Can you see?
Yep, you're great.
Okay, awesome. So, so here's me doing science. I'm a research scientist here at SNOlab and working on. I work on the neutrino experiments that are here, but I'm going to tell you a bit about the dark matter experiments. But first, I want to talk a little bit about Dr. Jim Peebles. So he is a scientist working in the US, but originally from Winnipeg, Manitoba. And he just won the Nobel Prize with 2 other scientists for his work on postulating why that dark matter is so important in our universe, what it does, and that it would make such a difference, that it's the dark matter, why it's so important to the formation of the universe. So I wanted to give a shout out to a Canadian here. But what dark matter is still an open question in science. We still don't know yet what dark matter is, but we know what it does. So here's a picture of a galaxy, and the galaxies spin, they rotate around a center axis, just like our solar system does. But the stars in the outside of the galaxy are spinning way too fast. They should be flying off, but we don't see the stars flying off. We see them rotating normally around in the galaxy. So it should be like if you're on a merry-go-round, as you see in the corner in the bottom. If you're spinning too fast, you have to hold on really tight to the side to not fall off. If the dark matter is like that pulse of you holding on, we know that the stars don't fly off the end. So there must be something holding them on. And this something that we don't see that's holding them on is what we call dark matter. We can also see dark matter bending light. So the gravitational force, so we know it pulls the stars in together in the galaxy, and we know that it can bend light. So you can see here this this picture of, it looks pretty much like a smiley face, which is why I picked it, that the edges of the light are kind of bent around. So dark matter can deform the path that light takes. We can see its effects, but we still don't know what dark matter is. We know it's we think it's a particle. We have some general ideas of what it should be, but this is what we're doing at SNOlab, is searching for dark matter. So this is a picture, not right now. Luckily, it's not snowing up here yet, and you can see in the inset map where we are in Ontario, just north of Georgian Bay. But we have many different experiments that are looking for dark matter. We started as a neutrino laboratory, looking for neutrino properties, and neutrinos are other awesome fundamental particles that I could go on and on about, but this being dark matter month, I thought I'd try and keep it together. The lab is in an active nickel mine. Creighton mine has been around for 100 years. In this picture, the red is the ore body where we have taken the nickel from. And we just happen to, oh, here's enough, be able to grab a corner of the area and build this international particle physics facility, looking for neutrinos, but also looking for dark matter. So here is a picture of the lab. It's about the size of a shopping mall, 5,000 square meters or 54,000 square feet total in area. And where each of the stars are 5 of our dark matter experiments, ones that are either under construction or actively running and looking for dark matter. And we have a couple other neutrino experiments like I mentioned, but maybe we'll talk about them during neutrino month. So looking for dark matter, we have a couple of different techniques. The DEEP experiment uses liquid argon. So argon is on the periodic table and the noble gases side. They cool it down and use this to look for dark matter to bump into one of the argon atoms and cause a little bit of light. The NEWS-G experiment uses helium, so another noble element, also looking for an electron release when a dark matter particle will hopefully hit into the helium. The PICO experiment uses a superheated refrigerant like Freon, looking for a bubble to form when a dark matter particle bumps into the refrigerant and the nucleus of the refrigerant. The Super CDMS experiment uses germanium and silicon crystals and they look for electrons to be released when a dark matter particle hits one of those. And finally, the DAMIC experiment uses what's called a CCD. It's the same kind of sensor that's in your cell phone camera or any digital camera to look for the tracks that are left when a dark matter particle interacts in their detector. So we have many different experiments looking through many different ways of trying to understand what dark matter is, really all over the board, because we're still looking for this. With 2 experiments on the way too. There's a similar but different experiment using CCDs and another bubble chamber like PICO, but that will produce light also. So it's kind of a combination between the DEEP experiment and the PICO experiment. There's just so much coming on at SNOlab for studying dark matter. And again, we're 2 kilometers underground. This is the perfect place to study the heavens and the cosmos, is from deep underground. So one of the questions we often get, and hopefully something you'll ask me, is what do we do with dark matter once we find it? Well, we know that we can tell from the work that Dr. Peebles did that it makes up 27% of the universe. Everything that's out there, 27% of it is dark matter. The light that we see, the stars, everything that we can see in the universe is only 5%. So we're trying to understand what is this, the rest of the stuff in the universe. What is it made of? What properties does dark matter have? Once we understand this, we can start to understand how the universe is held together. Why is it that we have this dark matter, and how do the galaxies not fly off? We can see, does the particle that we've discovered really fit in with what else we know about particle physics? We have all of these models that describe everything we know really, really well, but dark matter hasn't quite fit in there yet. So we're hoping that once we understand it, we can try and fit all of the new rules together. And with everything in science, once we answer a question, it gives us more questions. And we think we understand things, and it turns out that there's so much more to understand. So this is what we're hoping to learn at SNOlab. Part of the research we do at SNOlab is dark matter research, and this is it's the best place to do this kind of research. I'm now.
You're trying to get the screen done, share?
Yes. There we go.
There we go.
Okay.
Perfect. So, okay, so you're done. I'll dive into with
Yep.
Q&A. That's great. Thank you so much, Dr. Caden. That was fantastic. So we've got a bunch of groups watching on YouTube. I know a lot of kids in Laurel Springs School are watching. So if you want to ask questions directly to Miss Wafer, great. If we have other teachers watching, just type in your questions in the chat bar. Let me know where you're from, and I'll happily pass them on. But for now, let's dive in by starting with Miss Cooling's class. If you guys want to kick us off with a question, come on up.
How are neutrinos measured at the lab?
Yeah.
So how are neutrinos measured? So when we say that we're measuring neutrinos, we're looking for the little flashes of light that are produced when a neutrino hits another particle. So a lot of our detectors, the deep detector that I showed the back of it, the big copper one, they're covered with little light sensors, little maybe 8 inches around, 20 centimeters. So when a particle interacts, there's light that's given off. And so we can add up the light that is seen by all of these light sensors, and that tells us how much energy the particle has. And through different interactions, we can expect which particles are interacting. And by measuring the energy, we can then know which ones we see.
And I know it's Dark Matter Month, and I know the first question was on neutrinos, so I want to ask, just for the kids who might not know what a neutrino is, and just explain it really briefly.
That's a good point. So neutrinos are also fundamental particles, like we think dark matter is. Neutrinos are similar to electrons, but they don't have any charge the way that an electron does as it orbits the nucleus of an atom. And neutrinos are much, much smaller. So they are produced in any kind of natural nuclear reactions, natural particle decays. Fusion in the sun produces neutrinos, and we can produce them accelerators. We can make them, they're a byproduct from nuclear power. They don't do anything to us. They fly through the earth, they fly through us. If you hold out your thumbnail, every second, even 2 kilometers underground, you have 100 million neutrinos just from the sun flying through your thumbnail every second. So they don't interact with anything, but they are fundamental to how the universe formed. When we have stars explode, when stars go supernova, in certain kinds of these explosions, you get neutrinos coming out. And they actually help the explosions happen. So they're fundamental particles, just like protons and neutrons are. But because they're so difficult because they pass by, they're very difficult to detect, and they're very difficult to understand what their properties are. What do they weigh? Other properties like that. So that is the other half of the research, the particle physics research we do here at SNOlab, is trying to understand neutrinos. So the original SNO experiment showed that neutrinos oscillate or change, how we call changing flavor, that changes some of their quantum properties as they come from the sun. And so the leader of the SNO experiment, together with the leader of a Japanese experiment that showed something similar with neutrinos from a different source, got the Nobel Prize in 2015 for this research. So because of building that experiment, and then we created the lab after to house more experiments that needed to be deep underground to do their research. That's why we're here today.
Very cool. All right. Nobel Prizes coming out of that place like nobody's business. All right. Miss Eugenio's class, if you guys have a question, go for it. Come on up.
Okay. All righty. What would you do if you don't find dark matter?
The ultimate question.
That is a great question, because so far that's all we've been doing is not finding dark matter. So then we have to go back to our drawing books and think, well, can we build a detector that's more sensitive, that we can see interactions of smaller and smaller energy? Do we have to rethink the interactions that we're looking for? So I talked about how it can hit freon and make a bubble, or hit argon and make some light, or hit a crystal and free an electron and detect that electron. So we have all of these different ways of looking for dark matter. Do we have to come up with another way? Are there other interactions that we should be looking for? And all of our experiments are looking for a certain kind of dark matter candidate particle called the WIMP. Are there other weakly interacting massive particle, because we love our clever acronyms as physicists? Is there a different kind of dark matter particle that we should be searching for that will have different interactions? Those are the questions we start to answer. Should we be even deeper? We don't think being much deeper than SNOlab would make too much of a difference. Or do we just need to build bigger detectors and have more possibility for interactions to happen without the other backgrounds that come in that fake the signal that we're looking for? These are all questions that we're still asking ourselves because we still haven't found it. Like I said, we have 2 new experiments that will be coming online in the next couple of years that use similar but different technology. So every few years, we're stepping up how we think we should be looking for this.
Very cool. All right. Ms. Wafer, if you want to pass along a couple questions or one question to start from your class, go right ahead.
Okay, I actually have 3 that are kind of related. Alex is in North Dakota, 6th grade, and wondering actually why it's called SNOlab. And William is in North Carolina in 8th grade, wondering what kind of education you need to be at SNOlab. And then Larissa in Florida, why is it underground? So we're new to this, so we have some basic questions. I hope that's okay.
No, that's perfect.
So, okay, why are we called SNOlab?
Yep.
So the original experiment was called the Sudbury Neutrino Observatory, and we're in Sudbury, Ontario. So SNO, and the Sudbury Neutrino Observatory Laboratory, because it had been a single experiment and has now expanded into a large lab space. The other questions, it was, why are we deep? Why are we deep underground? So the Earth, we use the 2 kilometers of Earth to shield our experiments from backgrounds. So the normal radiation that we get from the sun, the heat from the sun, cosmic rays, other sources of background that you have on the surface, all of those particles are stopped by 2 kilometers of Earth, or greatly reduced by factors of like 100 million, so that we can build these very, very sensitive experiments. It's like listening, we're trying to listen for a pin drop while an orchestra is playing. So if we come deep underground, then we can't hear the orchestra and we can just hear the pin drop.
And then what kind of education do you need to get this role? Yeah.
So I have my PhD. I was in school for a very, 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 very long time. We have many different kinds of positions for people with all different education levels. So we take in summer students. So these are undergraduates who have had maybe a couple of years of university experience and want to come and get some more research experience. We have engineering staff too. So we have engineering co-ops and then engineers. There's about 100 people, maybe a little over, employed by the lab. And there's all different jobs that we need to do here. It's not just only scientists walking around. We need much more than just scientists to build these projects. We have an IT group and engineers and millwrights and electricians and systems operators to run the process plants that we've built to clean the water and to clean the different fluids that go into the detectors. And then cleaners, people to physically clean everything that comes into the lab, because we're in an active mine. And so it's full of dirt because we're underground. And that dirt, the rock dust, would cause backgrounds inside our detectors. So we need to make sure that nothing that comes into the lab has any dirt left on it. So like myself, I have to take a shower every time I get underground. When Jesse visited last year, he had to take a shower. Every single piece of everything you see behind.
Oh, if Erica's still there, don't move the computer. Yeah, okay. Give me 2 seconds. I'm going to bug Erica because she cut out there. See, this is what happens when you move a computer 2 kilometers underground, like 2 inches, is that it throws out the whole signal. That's hilarious. I'm going to email her and see if we can get her back in a second. And then we'll be good to go. Okay. Half the fun of doing things in remote places is that sometimes there's many technical difficulties. Give me 2 seconds. bug her and we'll get her right back. All right. Oh, not yet. Sorry, guys. Give me 2 quick seconds and we'll see if we can nab her again. Erica, I don't know if you can hear me still, but your connection is entirely gone. So we're gonna.
I'm back.
Oh, you're back. Oh, good. Okay, perfect. Welcome back. That's funny. You moved your computer 1 inch and it died. Okay, so now we know. You were talking about getting into the mine, which is actually something I was going to ask you next.
Oh.
So you were describing, yeah, you were back at the point where, you know, when I came in, I had to take a shower, and then you were describing a little bit more about the process getting in, I think.
Yes. So everything that comes in has to be washed. Every one that comes in, and every piece of things. I won't move my computer again to show. So that, and the people that do the work to clean all of the hardware that comes in are a huge asset. We couldn't run the experiments without the help of the cleaners. So there's many different levels of education, I think is where the question came from, that you need to do all the different jobs here. So we have about 8 research scientists and maybe 5 postdocs and a number of graduate students and undergrads that come in to work on the experiments at different stages.
Very cool. By the way, when noise comes out there, we don't really hear it too badly, so don't worry about that, I promise. All right, Ms. Meineke, we've got a kid waiting right there, so I'm going to go to your class next. If you have a question, come on up.
I'm Elizabeth. My name is Elizabeth, and my question is, why do you not want radiation from the sun?
So that's a really good question. So it's really that everything else, the sun isn't as big of a background, it's everything else. And the things that we do want from the sun, the neutrinos, their signal is not as strong as all of the signals from everything else. And for little things like light, all of our detectors are completely dark inside, because the particle interactions that we're looking for produce small amounts of light. So we don't want any other light to cause signals. A lot of our backgrounds actually come from things like dust, dirt, and any inherent radioactivity in the materials that we choose. Again, nothing super dangerous, nothing like Hulk or Spider-Man radioactivity, but anything that would cause a signal that's not the signal that we want to see is then too hot for us.
Although I must say, I'm very disappointed you don't have Hulk radioactivity down there, but that's okay. What can you do? All right, Mr. Candella's class, if you guys have a question, come on up.
David, light on, please. Lily and Noah, come to the front of the camera. There.
You're good.
Yeah.
So we have 2 questions, one basic question and one more in depth. So the first question would be, why do you want to know how much dark matter there is or where it is?
And Jeffrey Nolan.
And the other question would be, why don't you send a probe to outer space to get even further away from the sun, rather than, or just round to the other side of the Earth to further yourself from the radiation?
Yeah.
Nice.
So those are good questions. So we want to understand more about dark matter because it makes up such a large fraction of the universe, and we have such a limited understanding of it so far. So for the basics questions of science, we want to understand more. We want to know more always about everything, and especially something that is so important to the formation of the universe. We are still we're still trying to understand how things formed after the Big Bang. We can go back pretty far in time and understand things, but not all the way back. So we think that understanding more about dark matter will help us answer those questions. As for getting away from the radiation, there's actually a lot of radiation in space from old star explosions and from just particles whizzing around in and out of the atmosphere. So that's something that astronauts have to be aware of when they are in space, is that just ambient radiation is at different levels. And if we were on the other side of the Earth, eventually we would be at the sun. So going into the center, not quite the center of the Earth, but deep into the Earth is the best way on Earth to block all of the other radiation. Those are great questions.
Very good question. It's actually been really highlighted a lot during our space month, is the fact that if you go into space, if you go somewhere like Mars without an atmosphere, there's a ton more radiation. So that's actually a big issue in terms of exploration of space. Excellent. We had Mr. Hull's class join us, grade 5s in Canton, Michigan. So I want to go to them for a question. Come on up, guys, if you're keen.
Is dark matter required for life to exist?
Sorry, could you?
Hey, is dark matter required for life to exist, Erica?
Oh, that is a good question. So on a biological level, I would say no, but we need it to make sure that our galaxies stay together. So one thing that might have been explored this month is how the Earth seems to be just the perfect distance from the sun, that we're not too hot, we're not too close, so it's not too hot, and we're not too far, so it's not too cold, and we spin around at just the right angle, so we have seasons. So if we didn't have dark matter in the galaxies, there would be a different force on the Earth, and we might not be at the right distance. That's a great question.
Really good question. Very neat. All right, we have time to go through a second round of questions, guys. So what I'm going to do is start again with Miss Coolin's class. If you guys want to come up, go for it.
So basically, is dark matter only being studied based around like the particles that surround it and its environment and like the properties of those particles?
So that's kind of how we look for dark matter, because we are still figuring out exactly what we're looking for. We are looking for it to bump into one of the particles in our detectors. So we think that as we're traveling through space, as the Earth orbits the sun, we are half the time flying with the dark matter and half the time flying against the dark matter. So we would also think maybe there's an annual variation in the rate that our detectors see, which you would think may be really easy to tease out, but there's a lot of other things that vary annually. So that's a difficult way to try and claim that you have a signal. There are other kinds of experiments looking for other candidate dark matter particles that don't need to be underground. And there are other laboratories and other places in the world that are looking for dark matter. There's a lab in France, there's one in Spain, there's one in South Dakota, shout out to the South Dakota class. There's one in New Mexico. There's experiments in China and in Russia that's all over, that we're all looking for these particles because we haven't found it yet.
Yeah. By the way, I want to stress that this is probably the most dense topic that we ever cover, and you do a really good job of explaining this. So I know that some of the questions are difficult to explain to kids, especially in grade 5 and beyond, but it's really neat. So thank you so much for that. Quick question, follow up on that. Do those labs collaborate with each other? Do you all work together and talk?
Yes, so we talk at conferences and we all meet up and we all kind of know each other. It's not such a huge community. And some of us work on multiple experiments too. And we try to have experiments that are similar. So if someone sees the signal, we can verify it, but not exactly the same, because that would kind of be a waste. If we're looking for exactly the same thing with exactly the same technology, we should be trying different things. But we do all communicate and talk to each other. And you might do your undergrad research and experiment on one lab, and then do your graduate school research and experiment at a different lab, and then get a job at a third lab. And so you take all of the experience that you've learned from all of the different projects that you've worked on.
Very cool. All right. Miss Eugenio's class, if you guys want to come up for a second question, go right ahead.
If and when you find dark matter, what are you going to do with it?
What are we going to do with it?
Yeah. Nefarious
Celebrate.
Purposes. Yeah.
We'll probably question ourselves. So the way that we design our analysis of the data, we don't look at it. We try to do all of the math and the processing and try to understand what's coming out of our detectors without actually looking at the data themselves. So once we run all of the analyses, we're not trying to convince ourselves of finding a certain number. We're just waiting for the number to come out of the data, so that we haven't tricked ourselves into thinking that we see something that isn't quite there. So if we saw it, we probably wouldn't believe it ourselves at first, and we'd do a lot of double and triple and quadruple checking, and then of course tell the community, because this is how you verify that you are right. That, hey, this is what we did. This is what we think we found. Can you guys double check this? Can you make sure that we haven't missed something, that we don't that you've thought of something that we haven't thought of that could be causing the signal? And then we'll probably build another experiment and try and verify it. And, you know, maybe that's when you build the same detector in a different location to see if there's something in where the experiment is that we hadn't thought of that caused the signal. But at the end, if we're right, no, you just celebrate.
Very cool. It's actually been a really, really exciting time for physics, and I'm glad we got that question. I mean, in the last year, we found gravity waves, we found the Higgs boson, we took a picture of a black hole, all of which led to a lot more research and studying and information. But this sort of theoretical physics, this dense theoretical physics, leads to so many great things after it's confirmed and after it's done. Actually, I really would like you to speak to that, Dr. Caden. Just in terms of physics in general, this stuff seems very arcane, and the pursuit of knowledge is fantastic. But are there examples of where research like this has led to some developments that people would be able to use every day, or something that would, you know, impact them on a day-by-day basis?
That is a great thing to point out, is all of the technology that then comes from the experiments that we do here. So I mentioned the DAMIC experiment, which uses the CCD, charge coupled devices that are in your digital cameras. So they were originally developed for cameras on telescopes. And so now we use that same technology here, and you can use that same technology. There's a lot of technology that is used for cancer research. The proton accelerators that we developed for particle physics can then be used for more directed radiation therapy for cancer research. Not particle, yeah, I guess it's radiation therapy. Other things, so for the liquid that's in the experiment that I work on, SNO+, we are bonding a heavy metal, tellurium, into an organic hydrocarbon. Hydrocarbons, like mineral oil, they don't like to mix with anything, they separate. So trying to permanently bond a heavy metal, which also is difficult to bond onto an organic hydrocarbon, figuring out the molecules needed to make that bond happen. We've developed new molecules, new chemicals. So then part of our process has then been registering these chemicals with the International Chemical Society, so that we can have a number for all of our safety documents on what we've developed. And some of the cryogenic processes, some of the light sensing technology that we've done, those are a lot of the, and also the low background counting. So I talked about how all of our materials have to be very clean, clean on the outside, but also clean on the inside. So the techniques for seeing how radioactive a substance is can then be used for other technologies as well. And so that's just some of the things, but I think a lot of what physics creates is people. So the techniques that you learn in school for doing the research, for analyzing data, for questioning, learning how to ask the next questions and how to make sure that how to find the next best question fastest. Because you might ask silly questions. I ask silly questions all the time, but getting to the good question fast, learning those techniques and then applying them to other things, applying all the data reduction and analysis techniques that we use to big data to find to analyze data, to find trends that are useful in things like analyzing big healthcare data sets to find out, is this drug working, or are there other side effects that you might not be able to find with with small groups of data. If you have big data sets, then you can use these analysis techniques. Teaching people how to do that and how to apply these things in other fields, I think, is a lot of what physics contributes. Yeah.
Yeah. Excellent. So not only does the technology that we need to do these big experiments lead to great things, but the results of those and the people that come out of that process really contribute to society in a big way. Marvelous. All right, let's go back to Ms. Wafer's class. If you guys have a question, come on up and you're good to go.
Okay, great. So our students are just fascinated by the fact that you're looking for something that you haven't found and you're getting up every day and looking for it. So there's a few questions. Annalie in Fort Lauderdale, Florida is in 10th grade, just wondering how long you've been looking for it. And Tyson is in Mexico City wondering why you call it dark matter. And Henry in 4th grade in Florida wants to know, how do you know it's there? But most importantly, I think we're curious as a scientist, how do you wake up every day and look for something that you haven't found? What is your motivation and maybe what little successes do you have that keep you going? Because I think that's really helpful for young people to know for sure.
Cool.
Yeah. It's called dark matter because we know it exists. It's matter because it feels the effect of gravity, and it's an attractive, it's a thing. And it's dark because it doesn't produce any light. Oh, that's the thing I guess I didn't mention, is that it doesn't interact with the strong the strong nuclear force, and it doesn't interact with the electromagnetic force. We don't see it. It doesn't produce light, so it's dark. And I guess this is one of the things where we didn't come up with a super clever name and just call it dark matter instead of light matter. But how do we get up every day? How do we stay motivated? That's a good question. So we have incremental process in building these detectors and in searching for, and just in the experimental process. So we know that we're building something bigger. And so part of it personally is I know that each step that I've accomplished towards the big goal is a big step. So just kind of developing, knowing that and it's really one of the things I like about doing science like this, that it's not just me working on these big projects. Each experiment at SNOlab has, probably the smallest ones have 20 people working on them, and the bigger ones have about 120 people working on different aspects of the experiment. So one group in one university will be building a system to calibrate or to understand our detector better. One group will be working on the system for the electronics and reading out our data and processing that into bits that we can then read in our computers. One group is working on the chemistry of bonding those molecules together. So there's lots of different people working together on each step. And so I think part of it is you don't want to let down your colleagues. You want to all do your best work together. And you will probably work on maybe 5 or 10 experiments, maybe over the course of your career. So you will have, obviously you'll have some good days and some bad days, but you can see the successes that other people have had, and it's not like a slight on yourself that you haven't had them. You know that the field is moving forward and we're all learning the better questions to ask. I hope that answers the question.
Yeah, it's marvelous. All right, let's do 3 more questions before we wrap up, guys. We're gonna go to Miss Meinecke's class first, and go for it, guys. And let's get them in. Hey, Miss Meinecke. You guys, your audio isn't working for whatever reason again. I don't know what happened. So we'll come back in a second, mess with the computer, and I will go to Mr. Candela's class first. And worst case, if you have to type in the question, there's a chat bar on the bottom of the Zoom screen. You can type it in there, but hopefully you'll get your audio working. For now, Mr. Candela's class, go for it.
So,
Yep, you're good.
why do you wear protective gear? Like, we noticed you have a helmet and glasses, and just pointing out, we're gonna sign off after this. So thank you for your time and
Yeah. Awesome.
So I mentioned that we're in an active mine. Part of the safety aspect is that when I'm walking around, yes, I have to wear a hard hat and have to wear safety glasses. My shoes have steel toes in them, And this is just for doing any work inside the lab because it's still kind of an industrial setting. If I was sitting down at a desk, I wouldn't have to wear the hard hat, but then I would leave it at the desk and forget and walk around and be unsafe. So I just leave it on all the time.
Perfect. We can solve the mysteries of the universe, but we forget our helmets. That's the key. Miss Meige's class did type in the questions. They wanted to ask, why did they stop the nickel experiments, the original, I guess, Sudbury neutrino experiment?
So the mine that we're in is still mining nickel. They are still taking ore out. When I came in today, I talked with one of the geologists. It's still an active mine. They stopped the original SNO experiments because they found the number they're looking for. So one of the things in designing your experiments is you understand its response and you understand how long you have to run to have the precision of the answer of the question you're trying to answer, if that makes sense. So once you've run for a certain amount of time, you know that no more statistics, getting more data isn't going to make your answer any more precise, that the other backgrounds in your detector are now the limiting factor in reducing your uncertainty on your answer, which is a factor of all experiments. So they found the number they were looking for beautifully and verified it in 3 different ways and kept evolving the detector. It was a really great experiment. But then they found their answer. So that's now the experiment that I worked on, SNO Plus, is reusing that hardware, but again, with a different liquid inside, looking for different kinds of neutrino interacting. There's a lot of recycling going on in particle physics.
Very cool. All right. And then we'll wrap up with one last question from Mr. Hall's group. Come on up, guys.
Come on. Eric, go ahead.
Eric.
Oh, he wants to come on. Go ahead, Eric.
Is dark matter super toxic and can it wipe out a country?
Super villain dark matter plans.
Villain dark matter. I like it. Maybe that'll be my Halloween costume. No, we don't think it's toxic. And I don't think it could wipe out a country, but don't tell the Hollywood writers that because they like to use it for movies.
Yeah, all right. And with that, Dr. Caden, can you, before we wrap up today, is there any last message you want to share about how kids can learn more about what you guys are doing at SNOlab, about dark matter generally, anywhere we can point them to learn more once this session's done?
So there is our website, snolab.ca, where there is some information about all of the other experiments. And there's a link to the Dark Matter Month Interactions webpage that all over the world are different events for Dark Matter Month. So I think there's a group from Kingston. There's a talk, I think tomorrow night, as Astronomy on Tap. Queen's University is involved in a lot of the experiments here. And they have the McDonald Institute there has a great outreach program for public talks and trying to make sure that the public knows what we're doing here because it's so interesting and because everyone should be more science literate. We love talking about the work we do because it's so important to us. And like we said, it can have implications on your life too. So you should also know about it.
Outstanding. Well, we'll be sure to share those resources with all the classes when we're done. Thank you so much, Dr. Caden, for joining us today. And as always, what we're going to do is I'm going to demute everyone's microphones. So boys and girls, if you guys could get ready to join me in saying a huge thank you to Dr. Caden for joining us today. You are all now demuted. Go for it. Thank you guys so much for joining us today. And for the new classes too, we had a bunch of new classes. This is really exciting. Trial by fire. We start with dark matter with Exploring by the Seat of Your Pants. I appreciate it. Dr. Caden, thanks so much for joining us today. It was always a pleasure.
Thank you, Jesse. This is always a great experience.